right? That's the intermolecular. But when you deal with, so intermolecular is here, but now you've got, let's say, the hydrogen going to the oxygen. This is a hydrogen bond. This is going to be, I'm sorry, this is intramolecular, and then this is intermolecular, all right? And you can see it where it kind of creates this three-dimensional kind of figure by putting these hydrogen bonds. Hydrogen bonds are going to give you that, that structure, but they're very weak. We could break those. And this is just a close-up of a nice summary of it all. Covalent, intramolecular, hydrogen bond, intermolecular. Okay? Difficult to break up, easy to break up. Okay? Go ahead. About atoms and bonds and, all right? I'm really giving you a crash course of the whole chemistry course out there, and we're doing it all in like one day, 2.5 hours. Okay? So, it's a lot, but I'm really just giving you the meat and not the fat first. Okay.
What time are we going to be done?
Hopefully by, you won't go to 2 o'clock, so between 1 and 1:30. Yeah, okay. All right, so chemical reactions. So chemical reactions is now we need to either break bonds or we have to make bonds. That's what chemical reactions are, okay? And it's symbolized by a chemical equation where we're going to have reactants with a yield sign, and then you got products. All right? We're going to see this often. So we have classes of reactions, and this is really self-explanatory when you see the pictures. We have decomposition, where we're going to break bonds. If A and B has a yield sign, and then you got an A and then you got a B, large to small. You have synthesis, where we're going to make bonds. You have an A and you have a B and put them together. Or we could also have an exchange, and it's pretty self-explanatory. You got a creature here, a creature here. There might be an intermediate process, and then the A and C plus B and D. So there might be something like that, some kind of exchanging going on. And here's just pictures just showing the same thing. We have a large molecule that we're eating. We need to break it up into small things so we can get absorbed in our blood. Or we got to build things, build muscle and molecules and proteins. As you saw with amino acids will go and form a protein. Or we can do some kind of changes, which later on you'll see when that occurs.
Can you see the other one?
This one? Yeah. Okay. Questions on this? All right. Now metabolism. We talked about this briefly last week, but metabolism is all the chemical reactions in your body, all of it. If we're going to make bonds, we call it anabolism, all right? Like anabolic steroids, we're going to get big and strong, okay? Okay. And in order to do this, you're going to have water gets released. We're going to have to remove water. Energy is going to be needed for this. So if we're going to remove water to add bonds, we call it dehydration. It makes sense, right? You're going to dehydrate it. Catabolism, like catastrophe, is when we're going to break down something, break bonds. And in order to do this, we're going to have to add water to it. But when we add water, we're going to have to take the water and cut it up into two with an OH and an H. So because of that, this is called hydrolysis. Hydrogen is going to, or the water, which is hydrogen basically, is going to break up. Lysis means to break up, so we call it hydrolysis. And energy or heat is usually released when this happens. So give you an example. This is dehydration, anabolism, where you're going to have a big molecule here and another molecule over here. We want to add a bond to it. So in order to do that, we're going to take an OH from one and an H from another, water. Water gets released, and then we can build a bond from here to here. Okay? So water gets released. That's why we dehydrate. We have to get the water out of there. Then we have hydrolysis. We want to do the opposite. We have one large molecule over here, but if we add water, There's going to be an OH from the water going on one molecule and an H that goes on another molecule. Now I got two separate things. That's catabolism. Hydrolysis is going to break up the water. Okay? Now we can see it that way. You know, I'm not going to ask you to draw molecules and these chemical reactions and stuff, but I want you to understand, and conceptually, I want you to understand what's going on. Whether we go anabolism, that means we're going to have water come out, dehydration, the two structures over here, or we're going to have catabolism, which means we're going to add water to separate them. When we learn about things with ring structures, when we deal with sugars, it works the same way. Remove the water, add the water, okay? So it doesn't matter what structure. I put examples in here. I'm not asking you to memorize what these things look like. Just understand where the water interplays with catabolism versus anabolism. Okay? Now, factors that influence reaction rate. In other words, how can we speed it up? How can we slow it down? We usually don't want to slow it down. We want to speed it up. So how can we speed it up? Well, we increase the temperature. When you increase the temperature, the reaction rate goes faster. If we take a block of ice and we let it sit there on the table, it will melt. But if we put it on the stove, it'll melt faster. Okay? If we decrease the particle size, the reaction rate is going to go faster. If we increase the surface area. Now, this is what surface area is. A lot of students get confused about this. Surface area is where something could attach to, so to say. In other words, if this is what we have, some kind of structure, the surface area is where something is exposed to on that item. Now, if I break this in two, I did not change the volume of this, but I did create two new surface areas. If I break it again, I created two new surface areas without changing the volume. So if heat could only go on, give an example like ice. If heat could only go on, could only attack on the surface area. If we increase the surface area, it's going to speed up. A good example of this is I take a block of ice and I put it on the kitchen stove. And then I take that same block of ice, the same size, and I turn it into ice chips. And I put that on the stove. Which one's going to melt faster?
Ice chips.
The chips, because there's more surface area even though the volume's still the same. All right? So do understand for the rest of A&P 1 and 2 what surface area is all about, because we'll be talking about that often. More surface area means there's more absorption, because there's more places that it could be absorbed on. Okay? If you increase the concentration, the reaction rate goes faster. If you add salt to water, you're going to actually speed up the the boiling. All right, the boiling. If you didn't know that, that's if you add a few, not a lot, because then the water's going to taste salty. If you're doing it for, let's say, making spaghetti or whatever, you need to boil it with the water. But if you add salt to it, it'll actually speed it up. If you add more salt to it, it'll speed up faster. But you don't want it to taste salty. Does that make sense? You got that little side effect of that. So if you add more concentration, the reaction rate's going to go faster. We also have catalysts. Catalyst is something you're going to add to something, and it'll speed up the process, but the catalyst is not going to change. So it doesn't get chemically changed. The salt is a good example of that. I'm going to speed up the boiling water by adding salt. The salt's not going to get ruined in the process, but it's going to be a catalyst. It's going to speed up the process. In our bodies, we have tons of these catalysts. These biological catalysts are called enzymes. And we have to have a lot of enzymes. Will our bodies break up things by themselves? They do. But it could take hours, and if that happens, you're dead. So we have enzymes that are going to speed it up astronomically. Something that would normally take 2 hours to metabolize, if you have a certain enzyme there, it'll happen in a millisecond. So that's what that is, enzymes. And that's why we need to discuss what enzymes are made out of, because it is us. If we have something that's going to break down those enzymes, we're going to be sick. If it has the last 3 letters as ASE, it's an enzyme. Amylase, kinase, maltase, these are examples of enzymes. So let's talk a little bit about enzymes. Enzymes, they're proteins. And after the break, we'll talk about what proteins are all about. They're organic substances. But we talked a little bit about it already, how the body can use proteins, but we'll talk about what it looks like. But they're proteins that function as these catalysts. They let the reactions go at a faster rate. There's a substrate that the enzyme must attach to do something. It'll lower what we call the activation energy. The activation energy, not to get confused with kinetic and potential energy, they're 2 different things. Activation energy is energy that needs to be created to get the reaction started. I know students have issues with graphs, okay? So I'm going to make this short but simple and just give you the nuts and bolts. In a normal reaction, for it to occur from here to here, we have to make sure that the reaction reaches a certain level. Once it reaches up here, the rest of it's going to be gravy. This point up here, this is energy level. Once it reaches this, then we can actually do this whole thing. It'll be gravy. So this is what we call, from the point of where we started to the point of where it has to meet, that is the activation energy. You got to put a lot in there to get it going, and then it just goes. What does an enzyme do? An enzyme is going to say, we don't need to have it going all the way up there. We're going to only allow you to go up to here, and you can just do gravy. Okay? If a baby needs to come inside here, into this room, which we can't do, but the baby wants to come inside here, it's going to be like, baby's going to walk very slow. And, enough's enough. We have to wait for the baby to come in before we start class or whatever. So we're going to have mom, who's the catalyst, is going to say, well, we're going to pick up the baby, we're going to walk her in. We just created the activation energy of the baby cut down. You see what I mean? She's the catalyst. Okay, so it can speed it up. All right, question about activation energy. All right, how a reaction does it? Okay. Now, enzyme action. A good example we're going to use is, let's say, sucrose. If it ends with OSE, it's a sugar or carbohydrate. We'll call it sugar. But this is a big sugar, and we got to break it down into 2 smaller sugars. So sucrose, which is table sugar, is going to break down into glucose and fructose. But it can do it by itself, but it would take hours to do that. So we're going to have an enzyme called sucrase to break up sucrose to speed it up. So instead of, you could read everything over here, but it's better if I just show you the picture. The enzyme is going to be this cloud. It's called sucrase. Sucrose, the sugar, is up here, and it's made up of 2 parts. But we got to break it up because sucrose is just too big to actually get absorbed into our intestines, into the bloodstream. It's just too big. So we're going to have sucrase, that comes from the pancreas, that's going to break that up at a very fast rate. It fits like a lock and key. This sucrose will fit perfectly into this sucrase little chair. When it sits in here, the enzyme is going to be able to break this up, and now you'll have the glucose and fructose come out, and now it can get absorbed into the bloodstream. Meanwhile, the sucrase is not altered in any way. So another molecule can actually go on the same enzyme and do it again and again and again and again. So after this reaction, this is still good. Okay, it doesn't get used up like a battery. And everything I just explained to you is on the slide before. It's just this is the picture form. Okay? And like I said, enzymes are not consumed, so they could be used over and over and over. And it does it with this, like I said before, astonishing speed, milliseconds. We also have cofactors. Cofactors are inorganic items, all right, inorganic items that are going to bind to some enzymes to make sure the enzyme does its job. Now, the difference between organic and inorganic, very simple. Anything with carbon that also bonds to hydrogens, but anything with carbon is organic, plain as that. If it doesn't have carbon, it's inorganic. Iron, that's inorganic. Sodium, that's inorganic. Okay? Sugars, lipids, all, and we're going to talk about that after the break, that's what's going to be organic. All right? Carbon dioxide is, even though it has carbon in it, it's not organic. Why? Because there's no hydrogen that the carbon binds to. Okay?
It has to be carbon.
Carbon has to be there, but to make sure to make it really organic, it has to also attach to hydrogens also. Okay?
Okay, so organic has to have a
Carbon, and if it has carbon, it has to be bound to somehow hydrogens. But I don't want to say all hydrogen creations, like water is probably the most abundant inorganic substance we have in our body. But it has to have carbon, and the carbon, some way in its molecule, has to be attached to some hydrogens. So cofactors are inorganic things that are going to help enzymes do their job. That's why we got to have zinc in our body, magnesium in our body, calcium in our body, copper, and so forth. We need small amounts of these, but enough to get the enzymes going. What's that?
Trace minerals. Right?
Trace, yep, they're trace. Trace meaning we're talking about less than 2%, in most cases less than like 1%. But we got to have these in here.
What are the examples of the organic partners?
Well, organic ones is coenzymes. Okay? So it's just the semantics here. Cofactors are inorganic stuff, whereas coenzymes are basically, they're organic, and they're usually vitamins because they have carbon in there and they're attached to some kind of hydrogen. These will also help an enzyme do its job. So basically, cofactors are inorganic that are going to help enzymes. Coenzymes are organic and are going to help enzymes. Okay? And these are usually some sort of vitamins. Okay? So it's just you don't have to memorize this, but I'm just showing you over here that glucose, in order for, let's say, this reaction to happen, glucose is going to have to use, let's say, NAD, which is going to be, a coenzyme, because it's organic. This is going to carry an electron from this reaction onto this reaction, and it's not shown, but there's an enzyme here that will do that. So it helps it. If we don't have this here, then this reaction really can't happen because we need this over here. Does that make sense? All right? You don't have to memorize that, but I'm just trying to show you where this comes into play. Okay? All right, let me do acids, bases, and I'll give you guys a little break. You okay with stuff? You glad you came in today? Because I don't think you want to do this by yourself, right? All right, acids and bases. Salt. Salt are inorganic compounds. Contains no carbon. They're basically cations other than hydrogen. So a salt is anything that, not a salt, that sounds weird, but like an assault, like assaulted someone. But salt is any cation that's not hydrogen And it can also be any anion other than, and I know it looks weird, but we call this a hydroxide ion. Okay? Anything sodium, chloride, potassium, phosphorus, they're all going to be salts. The only two that can't be salts are these. Okay? Electrolytes conduct electrical current. So they're basically ions that can actually conduct electrical current. If you have salt water, there's sodium, there's chloride, there's water in there. They're floating all by themselves, and they're looking for something that they could actually attach to. You put your hand in there, you could get electrocuted if there's electricity in there. All right? Distilled water, there's no salts in there. So I wouldn't recommend this, okay? But if you take a hot iron and you put it in distilled water, if you put your, electricity, you put your hand in there, technically, theory, you won't get electrocuted. I gotta be careful, especially I'm on tape, all right? But I'm just saying, because you don't know if let's say if you put it in a tub, you don't know if there's any salts or anything that's on there from the air that went onto the tub. Even though you have distilled water in the tub, you don't know what's on the tub itself from before. And if there's some kind of salt that's on there, you put your hand in there, wow, all right? So I'm just saying, in theory, in a closed, controlled environment, if you have that and you're really watching things, distilled water does not conduct electricity. An electrolyte is an ion. Okay? It has some kind of charge to it. And with that, it'll conduct electricity, some kind of electrical current.
Electrolyte?
Electrolytes. It's an ion, basically.
I have no idea. Yeah, there was something that my son's pediatrician prescribed.
Yeah, because they're probably very low in their bodies, right? If it's a lot of people like Gatorade.
Yeah.
To me, Gatorade is orange flavored sweat. Okay? What it is you're, if you're playing football and stuff, you're sweating a lot. You're losing a lot of electrolytes because it goes in there. So we got to replenish the electrolytes in you. Otherwise, you're not going to be able to, do muscle contraction, nerve conduction, and so forth, because it needs to do this electrical current. So we're going to replenish it. Now, if you put too much of it in you, big deal. You got good kidneys, you'll pee it out. You know what I'm saying? So it doesn't matter. You got good kidneys, it'll just get rid of it. Okay?
What did you call this?
This is a hydroxide ion. This is a hydrogen. Okay? So again, salts are cations or anions other than hydrogen ions or hydroxide ions. Okay? Now, an acid. An acid, when dissolved, when you take an acid and when you dissolve it in water, when you put it in water, it releases hydrogen. If it releases hydrogen, it's an acid. A lot of hydrogen, it's a strong acid. A little bit of hydrogen, it's a weak acid. Either way, it's an acid. All right, so if it releases a lot, it's that. All right, and a strong acid is going to conduct electricity much better than a weak acid. That's why if you put your finger in hydrochloric acid, which is a strong acid, you're going to burn your finger. It develops as electrical current and it presents itself as a burn. Okay? Now they have a complete dissociation. I'm going to show you a picture of that in a moment. Okay? A weak acid releases less hydrogen, and it's a partial dissociation. It's kind of like a 50-50. I'll show you what I mean by that. There's an equilibrium and it's reversible. So let me show you what the picture looks like. Here's a strong acid, hydrochloric acid. When you put this in water, it will dissociate completely. It will break up into hydrogen ions and chloride ions. All of it. A complete dissociation. You put this in here, and when you put it in water, you'll have 100% of this and 0% of this. And you can tell by the yield sign. It all goes that way. Now, let's hold off with that one. Here's a weak acid, carbonic acid. It's going to go and separate into hydrogen ions and what we call bicarbonate ions. But it's only going to go 50% there, and it's going to stay 50% here. It's because the yield sign can go both ways. Now, this is a very important reaction. So let's talk about this one. H2CO3 yields, oh, I'm sorry. Let me do it this way. This you're going to be using quite often A and P2, so I want to make sure you master this part. It's kind of fun. Good point. All right, so we have CO2 plus H2O yields H2CO3 yields H plus HCO3. Okay, so what's happening here? Carbon dioxide, when mixed with water, is going to create an acid, a weak acid, called carbonic acid. Okay? But this doesn't like to stay in this position. It's an intermediate. And it goes to this, but immediately will dissociate to here. And it'll go into hydrogen ions, and this is called bicarbonate ions. I'm going to abbreviate by saying bicarb. This will lead to this. Okay? Now, you're going to get 50% of this and 50% of this. It's like a teeter-totter. And it's because the yield signs go both ways. So let's look at this. You're going to have 50% of the stuff here and 50% of the stuff over here. That's why we call it a partial dissociation, not a complete, because only 50% is over here. Now look what's going to happen here. Let's say